Hey, Matt 140, this is Dr. Roach. Let's keep going with our discussion of section 4.1, 4.2. So we've hit the topics of end behavior and zeros and multiplicity. Now we want to see the impact of a zero on the graph of the function. So this is a little bit tougher. Students struggle with it a little bit at first, but keep in mind this is not going to be too bad. Now this function is on a really small scale here. Negative 25 to 25 is pretty extreme. And so it'd be really better if we could zoom in on this a little bit. Let me just capture this. Capture this. And I'm going to make it a little bit bigger just so that we can see it a little bit better. Okay. Where did it go? Sorry. Here it is. All right, and I'm gonna make this bigger. All right. Now, this function right here has two zeros. Now, remember, the zeros affect the local behavior. The end behavior is determined out here. The end behavior is positive infinity, positive infinity. So this is definitely, as far as end behavior is concerned, it is a positive even power of x. End behavior is a positive leading coefficient and an even power for your degree. All right, so that is clear. Now, the local behavior determines those factors that we were talking about. So here are two of our zeros. We have a zero at -1 and a 0 at +2. The multiplicity can be figured out by looking at the graph. Now, sometimes it's a little hard to tell if the multiplicity is 2 or 4 or 4 or 6, but we can tell whether it's an even multiplicity for sure. And then if you compare two even multiplicities, sometimes you can make a determination of which one is which. In this case, because this bounces off the axis, that suggests an even multiplicity. Now this could be a quadratic multiplicity 2 bounce, but if you look at this one over here, this is much sharper than the other one over here. Higher degree multiplicities have a flatter bottom, and smaller multiplicities have a more steep. Their bounce is more curved. So since the -1 is flatter than the other, I'm going to go with the multiplicity 4 on it. And at the +2, I'm going to go with a multiplicity of 2. They definitely both have even multiplicity. So my first guess is that we have a factor of x + 1 to the 4th and an x - 2 squared. And we're gonna see on the calculator whether this is a reasonable solution. So here we go. Let's pull up our calculator. And we're going to type this in. So we have a root of x + 1, a 0 of x + 1, and we're going with a 4th power, and then an x - 2 for the root at 2 with a power of 2. All right, we're going to just do a standard window at first. So zoom Z standard, and then we'll adjust it here to get that -25 in there. All right, it's looking pretty good, actually. Let's change our window to, so we're keeping the -10 to 10. You can see x is -10 to +10. The y is what we need to change. So we're going to change this to -25 and +25. Graph it again and just see if it looks reasonable, if we're in the ballpark. See that flatness here? Looks pretty good. I'm going to turn on trace here. Pretty good, and I would say we are in the ballpark. Another thing that kind of can help you is if you look at the y-intercept. The y-intercept, it occurs at 0, and it's come back as a 4, and roughly it looks like we have a y-intercept of 4. That looks like it's in the ballpark. So I think we've done a good job, and that is a good answer to that problem. All right, let's try another one. Now this one has odd multiplicity, and sorry, I said odd multiplicity. It does have some odd multiplicity, but it has odd end behavior. Now the scale of this is really, really large. Negative 25 to 50 is really big. Let me grab a shot of this, and let's make it a little bit bigger. It just makes it a little bit easier. So let me paste this in here, and I'm going to cover up some of these words for the sake of seeing this a little bit better. Now, this function has it has odd end behavior with a negative leading coefficient, because we're coming out of positive infinity and we're leaving out of minus infinity. So this has got to be negative odd degree end behavior. I'll put EB here. End behavior. The end behavior is negative x odd. So there's got to be a negative up front. So let's go ahead and just put that there just as a reminder. And in the end, if you add up all the multiplicity, it's got to have odd multiplicity. Now there's two other important pieces. This is the local behavior. That right there is a cubic 0. And this one looks like a quadratic 0. Now, when I say quadratic, I'm talking about the multiplicity. It actually looks kind of like a quadratic function. That's why I'm saying that. So here we go. So we got the negative leading coefficient for the end behavior, and then we've got a cubic. Now that looks like it's at negative 1. So at negative 1, so this is a 0 at negative 1. X plus 1 is actually a 0 at negative 1 because you want it to be the opposite. But it needs to be cubic in its multiplicity. And then the at positive 2, we're going to put a factor x minus 2. So it'll be 0 at 2, but we want to put a quadratic 0 because it bounces off the axis and it's not real flat there. That's why we didn't go with a 4 or 6. So even multiplicities bounce off the axis, odd multiplicities cross the axis, and then the higher your multiplicity, the more flat it is as it goes through your 0. Anyway, this looks pretty good. We're going to pull up the calculator just to double check. So don't forget to put the negative up front. That's for that leading coefficient, x plus 1, and we're going to cube that. And then we've got the x minus 2, and we're going to square that. We're going to start with the window that we're on right now, and it's already looking really good. I'm very happy with it. Look for the y-intercept. Make sure the y-intercept makes sense, and it does. If you hit trace, see the y-intercept negative 4. It's about right. If you want to make your window a little sharper, we go out to 50 on your y-max, and it'll look a little bit more like this. That axis is really dark because I have my x scale at 1, but the x scale is really more like 2, 4. Let's see, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Looks like the x scale is 5. And that'll, not on the x-axis, sorry. The x scale is 1, but on the y-axis, the scale is 5. All right, so this is going to look a lot more like the graph there with the tick marks. So it's bouncing off at 2. It's crossing kind of with a flatness at negative 1. Anyway, that's 2 really good examples of finding polynomial functions by using the multiplicity of their zeros. Thanks for watching.